All right, let me start with another one here. How about chapter 36, number 38. And what this one has is a lens here that then has a cube, or I'll just say square because we're looking at it in two dimensions here. But there is then the 4 points of it. And it asks a lot of questions about this. And it's really trying to figure out here what it would look like. And of course, this 1 over P plus 1 over Q equals 1 over F. And then they say things like this. Let's see, the focal length, so F is 14 centimeters. And the idea here is what would the image look like. And we'll run through the numbers because that's what they ask here in part A. But learning what we've learned so far is we know that, looking here at the math, this is a set number. So things like if you look at this point of the square here, point D, where D is smaller than A, the two of these together have to equal some kind of constant number, in this case 1 over 14. So a small D, in other words, if D being smaller than A, would then make a bigger D. And so this, what they're going to call D prime, may be further away than what they may call A prime. And the points have 0 height, so when it comes to calculating how high the point is, the height of the image compared to the object, we would, just say, well, we're going to get some magnification, but these things don't get any bigger. They start with a height of 0, or put another way, the height of the image is the magnification times the height of the object. So if we say points A and D have a height of 0, no matter what magnification we get a height of 0. So we know that these are going to be along this line here. And of course, then we can calculating them by saying Q, and we would take 1 over F, we would subtract 1 over P, and then we would take the reciprocal of that. And so if we do that for point A, and so we'll say A prime here, or where is the Q of the A, which they call this the A prime. Let's see. And so I'm going to grab my calculator. And, I guess we need to read something else here about distances. They say somewhere here, the figure, converging lines, focal length, that form an image of a square, which has a height of CD of 10, and so they're saying this distance here is 10. It also means this distance is 10. And the distance of D is 20. So they're saying this distance here is 20. All right, and that's important here because if I'm trying to find A, I need to know that the point A is 30 away, so this would be a reciprocal of 14 minus the reciprocal of 30, the inverse of that, and we're looking at 26.25 for the position of A. And then the position then of D prime would be that same kind of math, the reciprocal of 14 minus, and now D is 20 away. And so this is 46 points, 7, and let's go 0.3 up here, how's that? And so that gives us how far away these are. And in fact, the difference between them, the 46.7 minus the 26.3, leave me with a distance of 20.4. And so that's the connection between the A and the D. So this thinking was how to figure out where the image is on, this, I'll call it the x-axis. And the same logic could be applied to on the y-axis. So what we're going to know is we're going to know that point B is going to be, from the distance, will be the same as A. We also know that since it's a convex and greater than the focal length, we can even see it here from the magnification. So maybe I will. So the magnification of the things at point A and the magnification at the things at point B. But you can see then that since the magnification has to do with the distances here, these ratios, that objects that are closer to the focal length, so the focal length right here about 14, and if you look at the map, things that are close to the focal length get blown up really big, and less so as they get further away. So the C to D is going to look something like this. It's going to be magnified more than something that's a little further away, actually quite a bit further away, because it's only 20, so it's a 50% increase than something that looks like that. And so we're going to get an image here that looks like a trapezoid. And so if we figure out then the magnification here on this distance A, and so this would be the negative of Q, so 26.3, out of that distance away, which, what did we say? A was a distance of 30. We get a magnification then of a negative 0.877. And of course, then to get the height, we take that magnification and multiply by how high it was. Well, A to B was 10, so if I multiply it by 10, we're talking about an 8.77 centimeters high. And negative, and so that was the part that I was saying, this would be upside down here. And so this is a negative 8.77 centimeters. And then over here, if we wanted to know how tall that was, we do the same thing, the magnification. So negative 46.7 divided by the distance it was is 20, and so we get a negative 2.34. So the height then, of course, times 10 would be a negative 23 point, and I'll just call it 4. So this would be 23.4. And I guess technically negative, but hopefully my picture shows that, yeah, clearly it's upside down. And so that's the idea here. Okay. Knowing all of that, we can now get, I think, the answer to A, or maybe I just did A. Let me look at A. Let A, B, C, D, and prime represent the respective corners of the image, and let QA represent the image distance, so then we'll put a little prime there. QA represent the distance of points A prime and B prime, and D time representing C and D, and H representing the distance, blah, blah, blah. Evaluate each of these quantities and make a sketch. Okay, so I guess I did. So I've evaluated all those and made a sketch. So this is all A. And then B says the area of the object is 100 square meters. By carrying out the following steps, you can evaluate the area of the image. Let Q represent the image, the object. Let H prime represent the distance from the object to the corner, and show that H is. Now that's interesting. I guess I would have thought that the area, they would have just done a trapezoid. But but that's not what they said to do. But I think I will nonetheless. I'm going to do a little trapezoid here because we know the area of a trapezoid is the let me call these the two different heights of it, but we average those two, and so 8.77 plus 23.4. And then we multiply by the height of 20.4, and so there's the area of our trapezoid. So 8.77 plus what I say 23.4, divide that by 2 to get an average, then multiply by 20.4, and we're looking at about 328. So 328 square centimeters square. Centimeters is the area of this trapezoid, the image. Which is, of course, much bigger than what they said it originally started with, would be 100 square centimeters. So it makes sense. It's magnified up. This has been reduced a little bit, but it's been stretched on this axis. So the image is much, much bigger, slightly different shape. And that's, again, the whole idea of this chapter is what would you see? And so this really illustrates point by point. What would you do with a point that is above the axis, below the axis, on the axis, close to the focal length, far from the focal length? And so these 4 points are all projected over to here. Now, back to the problem, because they didn't have us do it this way. They said prove that the height of the image, and they do absolute value, is equal to, and so I'm going to come back over to here, so it would be the magnitude of the magnification times the height. And in this case, then, the magnitude of the magnification times a height of 10. And the magnification is the, it's the Q over the P. But I'll drop the negative sign that we had back here because, again, they're just the absolute value of it. And then, of course, if we remember that 1 over P plus 1 over Q equals to 1 over F, which in this case is a 14. So I'll put 1 over 14. We could get rid of the, how about the P, because it looks like they want us to be left with a Q. So let me write this as 1 over P, then a Q times a 10, because the 1 over P, so 1 over the P, would be the 1 over 14 minus the 1 over the Q. So then this would be 10Q. I'll just put this first and change the order. And then the 1 over P is the 1 over 14 minus the 1 over Q. And I think that's what they say to find here, right? In B, show that it's 10 times Q, and then 1 over 14 minus 1 over a Q. So great. So there is the answer to B. And then C says, well, then explain why this integral would give you the area. And so I guess that's a calculus thing. But if I were to come over here and say, okay, so I could integrate and say, okay, this little rectangle plus this 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 rectangle plus that rectangle. And so if you added up all those, you would get the area. So in other words, the area is... And I guess you would, say something. See if I'm saying this right, but it would be the height then of this image, and I'll just do magnitude. And then if you added that up over all these different locations from here to here, but of course that's then from A prime to D prime is really this integral here of this DQ, I guess, is what we're really saying here is this little space here is, where is each of the image? And of course, then you would be adding it from the location of point A to the location of point D. And so that's our integral here. And of course, now they say, well, go ahead then and carry that out. Okay, so I will. And so this will be an integral. And so coming back to this equation, it is 10q times 1 over 14 minus 1 over q. And then as we learned earlier, the position of A, where'd it go here, is the 26.3. And the position of D is 46.7. Okay. And so, breaking these into its two integrals, this first one would be a 10 over a 14 and a q dq. And the next one would be the integral, and the q's would cancel off, so it's just a 10 dq. All right, so this first one would be 10 over 14, and it would be q squared over 2, evaluated from 26.3 to 46.7. And this next one then would be a 10q, again evaluated from 26.3 to 46.7. And so maybe I'll do this first term here. Maybe you can still see it here. Yeah, maybe let's put it up here. But this would be a 10 over a 14, also over a 2. So that's that first part. And then all of that is then times 46.7 squared minus 26.3 squared. And so that is 531.9. And then this one here would be 10 times, and then the 46.7 minus the 26.3, and that's minus 204. So 531.9 minus 204 comes out to be 328 square centimeters. And that does match what was a lot easier to do in just terms of trapezoid. Anything with a straight lines are much easier to get the area just using geometry than calculus. And and that's it.